Right, quick recap. We've got our linear system AX equals B, where A is symmetric and positive definite. And what we want to do is find a solution to X without inverting A. And we're going to do that with the conjugate directions algorithm for now, where we're going to start off with an initial guess at X, and then we'll iterate by saying that X at I plus 1 is equal to X at I plus a constant multiplied by what we call a search direction, D. And we're going to do that such that X converges to the true value, i.e. where AX is equal to B. What we did in the previous video is we derived an optimal solution for this constant alpha I. And we said that these search directions, we have freedom, if you like, over what they can be. And what we said was that if we chose them to be A orthogonals, that is, if di transpose multiplied by A multiplied by dj is always equal to 0, if I is different from j, if we can enforce that condition, i.e. choose our search directions so that this holds, then the algorithm is guaranteed to converge after n iterations. So we left it by saying, well, okay, how do we choose these Ds? How do we choose these search directions? So we're going to do this today with something that's called A orthogonal Gram-Schmidt. So we've already got a video on the Gram-Schmidt process, so it might be worth kind of looking at that before watching this one. With the Gram-Schmidt process, what we did is we started off with a set of vectors, let's say v1 to vn, that are linearly independent, i.e. as we've covered before, they just point in different directions, basically. And what we did is we started off by choosing v1, and then we used these vectors to construct a new set of vectors that are orthogonal. So we're going to do really a very similar process here today, but we're going to construct vectors that are A orthogonal. So basically, the key thing is we start off with this set of vectors and they're linearly independent. Okay, so they could just be Cartesian coordinates, or perhaps you generated them randomly. But the key thing is that these V's essentially don't point in the same direction. And we're going to start off by saying that our first direction for our conjugate directions algorithm is just going to be set equal to V1. Okay, so we have to start somewhere. We're then going to say that our second search direction is equal to V2, but it's going to be, we're going to add on a constant multiplied by D1, and we're basically going to see what we can do with this. What we're going to do is we're going to enforce the A orthogonality. So I'm going to pre-multiply, for example, by D1 transposed A D2. Okay, and then we're going to enforce that this thing is A orthogonal. So that means that this term here is going to be equal to 0. And then we solve for A. So solving for A, we see that A is going to be equal to minus D1 transposed A V2 divided by D1 transposed A D1. Okay, so now we have our first search direction, D1, and now we have a method for choosing, so we're substituting A into here. Starting from V2, we can now choose our second search directions, and by definition, i.e. because of this, it's going to be A orthogonal to D1. Okay, fine. So now we're going to move on and see if we can pick our third search direction. So we're going to say that D3 is equal to V3, and here we're going to have, let's say, another constant, call it a B, times second search direction plus another constant times third search direction. And basically we're going to apply the same trick again. So I'm going to start off by pre-multiplying by d1 transposed A, d3, across all of these. So d1 transposed A times v3 plus constant d1 transposed A d2 plus constant d1 transposed A d1. Okay, so again we're going to enforce our A orthogonality. So that means that that term is going to be equal to 0. We've already said, and by definition, we've said that D1 and D2 are A orthogonal as well. So this term disappears and goes to 0. And then we solve for the constant C. So we end up by saying that C is equal to, well, negative this thing. So that's a D1 transposed A V3 all divided by D1 transposed A D1. Okay, so we're getting there. And we still need to find our constant B, but as you can probably see coming, we're just going to use the same trick again. This time we're going to pre-multiply this equation up here by D2 transposed A D3. So I'll write everything out. So D2 transposed A V3 constant D2 transposed A D2 constant, which we've already found, but I'll just write it as a C for now, as a D2 transposed A D1. We enforce our A orthogonality. That means we can get rid of this thing. Again, we've already chosen our D2s and D1s to be A orthogonal, so this term disappears as well. And then we just solve for B, and we find that B is equal to minus D2 transposed A V3 all divided by D2 transposed A D2. Okay, and we kind of just proceed in this fashion. So what we're doing here is we're iteratively building up our search directions, kind of based on the previous search directions. And after a little while of looking at these equations, a general kind of expression emerges. So I kind of, let's see, I'll put it over in the corner here. So generally speaking, what we do is for our ith search direction, di, is we take the vector vi, and then we remove from it, well, we have a summation that goes, I'm going to use a j here, up to I minus 1, because we're actually removing the components of the previous search directions. So from j equals 1 to I minus 1. And we have a dj transposed A times, again, this ith vector vi, all divided by a dj transposed A times dj, all multiplied by the jth search direction. And so there we have it, really. In our conjugate directions algorithm, we know that if we use this approach here with A orthogonal search directions, we know it's going to converge after n iterations. And now, come down here, we've also got an approach for selecting those search directions that guarantees their A orthogonality. So the whole approach really is complete and kind of ready to be implemented. Okay, so here is an implementation of the conjugate directions algorithm. I've just written everything that's going on at the top here. So xi plus 1 is equal to xi plus constant times search direction. This is the A orthogonal Gram-Schmidt process that we've just derived. This is the optimal definition of alpha from the previous video. So down here we've got our conjugate directions algorithm. So I'm going to take as an input our initial guess at X, the matrix A, and then a matrix V. So in V, we can see that up here, because our A orthogonal Gram-Schmidt algorithm uses these vectors V, I've put them all just into one big matrix that I've written as a capital V. We know that for our A orthogonal Gram-Schmidt, we need to store all of our previous search directions to compute the next search directions. So I'm going to do that in a matrix capital D. Then we know that our very first search direction is also equal to the first vector V. Here we're going to compute the first residual. We need the residual because it's in our computation of A, which is written up here. And then we're going to let our algorithm run for n iterations. So first of all, we compute alpha, like we said. This is using the current definition of the residual, current value of the residual. We then compute our next x, so we don't need to store the x's. So new x is equal to old x, and then we've got an alpha multiplied by our current search direction. And then if we move down again, here we update the residual because we have a new estimate of x. And again, we have to do that because that's going to be used in the next iteration when we recompute alpha. In this case, we're going to run the algorithm for n iterations. So it should converge. It's guaranteed to converge as long as we've written it properly. And this is the application of our A orthogonal Gram-Schmidt process. We start off to find our new search direction. We set it equal to V. And then in this for loop, we are essentially removing the terms in the summation up here so that we get our new search direction. And I've decided in this case that we're going to return X because obviously that's what we want to find, but also the matrix of search directions D, just because it helps us do like a little check that the thing's working properly. So that's the algorithm. Here we're going to create an example system. So I've chosen n to be 100. I've made a matrix A that's positive definite, and I've picked the vector B randomly. To check that our solution is correct, I'm going to check against basically an approach where we do in fact compute the full inverse of A. So I'm going to say that x star is equal to, so here I've used NumPy's linear algebra module to compute the inverse of A multiplied by B. So we'll treat that solution as kind of the gold standard against which we can check our conjugate directions implementation. So we're going to run the conjugate directions algorithm. We said that you have to choose the V's so that they're all linearly independent. Here I've just picked them randomly, being a little bit lazy. For the initial guess at X, I've just set that all equal to 0, i.e. a vector with zeros. And then here we run conjugate directions to output our estimate of X, and also, as we said, our matrix of search directions. What I've done here, one of the things I want to do to just make sure it's working okay is to check that all of our search directions are indeed A orthogonal, i.e. check that the A orthogonal Gram-Schmidt process is implemented correctly. If it is, it means that the matrix D transposed multiplied by A multiplied by D should be diagonal. So I've just kind of plotted that just as a quick check to make sure it looks okay, and it does. And then finally at the end, we check our solution against that we obtained by computing the full inverse of A, and they are both the same or close enough. So everything seems to be working okay. A few things to note when we come back to this algorithm. First of all, if we look at here where we update the residual, what we've done here is we've deliberately said that we're going to run this algorithm for n iterations, and that's because we've done a proof that shows that it has to converge after n iterations. So that's fine. But you could also put in an early stopping condition. So you could, after this line that we're on, put in a condition that says if the absolute residual is below a certain number, then terminate the algorithm. So this shows how with conjugate directions, one of the useful things you can do is you can try and realize this trade-off between the precision of the solution that you're obtaining and the amount of time and memory that the algorithm takes. I.e., you can say, I will live with a bit more imprecision if it means I don't have to use as much memory and I don't have to wait as long, basically. A key thing to note is that, as we've already said, we do need to store all of our previous search directions to compute the next search direction, i.e. to implement the A-orthogonal Gram-Schmidt process. And as n increases, i.e. as we look at larger and larger problems, larger and larger data sets, basically in the context of machine learning, then this is going to take up more and more memory. So its scalability in terms of memory is relatively bad. For n points, we're going to have to store all of our previous n-dimensional search directions. Also, as we know, as we keep going, we're going to have to use more and more, run more and more iterations to achieve our A-orthogonal search directions. Or A-orthogonal Gram-Schmidt process has to run for more and more iterations. And so the conjugate directions approach isn't particularly scalable in terms of computational cost either. So in terms of cost and memory, it might not scale particularly well. But we are nearly there. What we're going to do in the next video to realize the conjugate gradients algorithm is basically all we're going to do is think carefully or more carefully about how we choose this matrix V, i.e. the kind of start points for the A-orthogonal Gram-Schmidt process. And what we'll do is we'll show with a careful choice of those vectors, what you can do is you can actually very much reduce the memory usage and the computational cost relative to the conjugate directions algorithm. So we're very nearly there. We've got all the basics kind of set up. We're really just going to show one more trick that gets us to conjugate gradients, and we'll show that that's actually much more scalable than conjugate directions.